Alright, these are the Russians in space in a vacuum chamber with charged particles. Now I'm just going to let this play and then I'll make a couple of comments here and there. Here it goes. Alright, this is what they're looking at, watching the actual particles. Alright, as they're doing what they do in, here it goes. Alright, the dust particles that are suspended within plasma. Plasma just means charges, heavy charges. So they're suspended in the plasma. Now, they get an electric charge and experience repulsion from each other. So everybody's supposed to push everybody else apart, so they're expecting to see them form in these like patterns in space in a lattice. And they did see this in a limited form. Alright, see this? You see the center ones? The center ones, these big ones, those are the actual nucleus. These are the actual electrons bouncing. Alright, because they're not settling in. Alright, because they're in zero gravity. Now, in orbit, the experiment, they accept the vacuum chamber has real space vacuum in it. So, what a real space vacuum means, out in space, there's no vacuum. Well, when I say vacuum, there is no empty space. This has no particles in it, in this little vacuum. However, it has particles that surround the encasement of it. So, those are pushing, and they're not taking that into account. Watch this. All right, so powerful computer used to process the results. That's the black bucket. And that's totally empty. Now they're injecting these particles. What are they doing? Watch what happens here. See them coming in stripes? Why would they do that? Well, that's because they push each other and shove each other away. That's what creates interference patterns. Interference patterns are not flapping this way and flapping that way. They are electrons pushing each other away, creating stripes. Now watch what happens when they fill this void. Alright, they get to the end, bang. You see all those stripes setting up? Now, they're watching them and they'll start to circle all around in there because there is no gravity inside there. So they're hoping to see them crystallize into this form, and then they're swirling all around and doing all kind of crazy things. And then they just start to, they figure, okay, now they're going to come up and see all this crystallization. Alright, so everything's going on in this black bucket. They received the data completely unexpected. All right. Now look at this. Instead of a clean lattice, everybody's pushing each other away. This is what they get. They get a black hole. Watch what happens. See it bounce, 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 bounce. You see this going boom, 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 boom. That's everybody's pushing each other, but they're pushing all the black stuff to the center. These are extra electrons in there. These are plasma. Plasma is charged particles. Charged particles means they have extra electrons. And in my world, an electron is both of these particles. It's the pushy-shovey one and the black matter. What they end up doing is putting the black matter in the center, and the pushy-shovey ones are pushing it in, and at the same time pushing away from each other. That's why these are not laying on top of each other. The blacks couldn't care less. They'll lay right on top. All right, so here's what they're seeing. They said they couldn't believe it. One guy freaked out. All right, one of the scientists from Max Planck Institute freaked out so bad that he locked himself in his office for several weeks. They don't know what to think of it, and then they just dropped it. Now, I made a whole bunch of inquiries at the same time. We got a lot of data just by observing the behavior of the particles. Yes, how do they behave, and why are they behaving that way? And now they're looking at them again, and they're doing all kinds of experiments. But the one I found most interesting was the one I just showed you. How they create that black hole in the center. All right, I'm not going to belabor this, but this is these are all at the same time, 4 different shots of the same event, and it appears to me that this is where the Venturi issues in, and then it sprays out from there. Now, which would be the pulsation waves coming this way, and then coming out is the spray of particles. Now, this lined up is I think the pulsations, I don't know. I have no idea, to be perfectly honest with you. I'm just looking at what I see, and I kind of understand what I'm seeing. They're going to line up and they're going to push and shove, push and shove, push and shove, push and shove. That's what it is. Now, if those are the pulsations of the actual laser, I don't know. Those could very well be as well. It's going to line up something like that. This over here is, again, these are all the particles in the way of the field. Let me show you what happened with ours in a similar situation. Now, I find this really interesting. As you saw the ones in space, they were straight up and down. Boom, 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 boom. Well, these are curved. That's because of the influence of the particles that are in front pushing back against what would have normally been a straight wave. In a vacuum, it would probably be flat straight across, just like we saw in space. But this is not a vacuum, and this is under gravitational influence in the presence of a ton of extra particles pushing back, creating the wave. The particle is back here. All right, the wave is out in front. The particle is the same particle that you see in the other cases here. All right, so the particle is here, coming through. It charges up. The top one will charge up, and it would flip to the bottom one. And now the bottom one would charge up, and it flip to the top one. That's how it does, but it's always going to be in this orientation. So the particle is way back here. The wave is way out in front. That's what particle-wave duality is all about. And the thing that's making the waves is these electrons, not big, huge protons. This is nothing more than light. They would say that this is just almost nothing. They don't even really count it for anything, to be honest with you. Light is the tiniest particle that exists within other particles. And the other particles are protons and neutrons and atoms. But light is atomic vapor, the atom of vapor, the vapor of atoms. It's like, well, let me show you something. I wrote this a long time ago. Okay, my friends, I took physics, I took atomic, everything, chemistry, and I loved all that stuff, and I got deep into it. This was right after I got out of the Army. I was in nukes and Nike Hercules missiles, and I got out and I went into physics and all that stuff, and I realized that nothing was right. I said that the transfer of energy from light to atomic vapor. That's what it is, atomic vapor. And there's only two types and they're all dipole to dipoles. Rutherford's atom was wrong. I got all into a big fight with everybody, to be honest with you, because I could not agree with what they were telling me to say. So I didn't get agree, I got a disagree. And I went on my own way. But we have all of this stuff very, very, very well documented now. And it's very simple stuff. Very, very simple. And it ends up right here with this. Muon neutrino, electron neutrino. The muon neutrino is the black ball. Never changes. To Don Lincoln at Fermilab, he calls that the fixed particle. This one, electron shower, is right here. You saw them black and white together. And then this black stayed just the way it was, never changes, and that's exactly what they say at Fermilab and CERN. And right through here comes a squirty little electron shower. Couldn't be any more obvious. And it's time to look at this look at it and just try to understand it, because we could maybe get free energy, almost overnight. I'm serious. Within months, we should be able to have this and using it to create extra electricity. That's what it's all about right there. Okay, this is fabulous, this little video. It's BrusPulp. It's called Amazing Resonance Experiment. Now, everybody that is in this page, I'm sure knows who Nikola Tesla was. Now, he's claimed that if you want to find out the secrets of the universe, you think in terms of energy. And energy is created by frequency and vibration. Now, they're saying it all is one big thing. But actually, I believe what he said was, if you want to think in terms of energy, think in terms of frequency and vibration. It's push to shove. And that's exactly what we're going to see right now. All right, if this doesn't freak you out, nothing will. I am going to show you right now brush pup here, this channel, brush pup. Amazing resonance experiment. They're taking salt and putting it on a table that they're literally shaking it, which is nothing more than electric up, down, plus, minus, plus, minus, plus, minus. And they're creating this frequency of hertz, which means how many cycles per second they're shaking. Now, I'm just going to run this. I'm not going to have any sound, but I'll be talking. So, NaCl is a polar molecule. It's on both sides of the periodic chart. Now, the metal plate vibrates. And what it does is it shakes. And you'll see them shaking. And then at a certain frequency, pip, they lock in. And the first frequency is going to be what I would consider hydrogen and helium, right there. All right, let's come open with this. Don't forget, brush pup. Now, this has just one core, and it has up to 4 possible particles in the orbitals. And that's exactly what hydrogen and helium have. And then you go up from there, from 345 hertz, they're going to increase the hertz rate, and you're going to see the rule of 8 come up, which means there's 8 particles surrounding the core. There it is right there. It couldn't be any more clear. 1, 2, 3, 4, 5, 6, 7, 8 surrounding the core. And then they just keep getting more and more complex. So what we saw was the very basic core, hydrogen and helium, and then you get into the rule of 8 particles. And then they get more and more and more and more and more complex until, and they get heavier and heavier and heavier, and more particles fill that space. Now let's, instead of going through each one of them, I'll come over here and there. Here's one here. All right. And as you go up, here's some more here, way up at, I don't know, whatever this is. Here's some more, 3975. And then they just keep getting very, very, very complex. All right, you see these? And they all have an exact pattern to them. Now, this could be, who knows, that could be copper, I don't know. Some of them are going to have some oddball characteristics that allow them to, like copper is a strange metal. There's a ton of extra electrons that just hang around. You see how complicated they get? Look at this. Isn't that amazing? And they just lock in at these frequencies. Boom. Look at it. It locks right in. Look at that. Absolutely incredible. Thank you, Brush Pup. Okay, my friends. We are going to have a fabulous time getting into physics. Quantum physics. This is Yale. Now, I always talk about going to school for free. You go to school for free. You don't have to pay. These are all the courses that Yale gives on the quantum physics. I mean, it's very complete. This is what they're telling the students. And the students are writing it down, and they're putting it in books. And this is what you have to do. And then when you go to a prospective employer, you come in with your book, and you say, I took all these courses. I didn't pay for them. And here's what I got from them. But you have to have some pretty good documentation. You know, a lot better than what for me, it's just for me. But when I was in school and so forth, I did all of this stuff. And I was still a mess back then, too. But what I'm getting at is, if you come in with something, you know, like I got chemistry, I got thermal chemistry, I've got quantum, I got all this stuff. Why should you pay somebody for the piece of paper? I've gone to all these. I've gone to, what was it, University of Geneva for particle physics. And I was able to interact with the professors and everything, and they saw my stuff, and they were impressed. But it wouldn't have been any difference if I paid them. They still wouldn't have done anything different. Because nobody really is interested, because they're hitting protons. We started with light, which is the smallest particle. They wanted to do this since 1978 and could not figure out how. We've done it, and now I think there's probably a taste of embarrassment, but I don't care about that. I just want to be able to see what we have discovered. What we discovered is that they're nothing but dipoles, and that the particles that make up protons are not just chunks of little bits and pieces of things. Every one of them is a dipole magnet. It's a little dipole magnet, just like that. Every one of them is like that. 2 of them together make this. Then you start to get into your full atoms. And then you get surrounded by the white matter. That's why we've never seen the dark matter. The only reason we see it is because of the experiments we did. And I didn't realize you could separate it, but we separated it. I'm going to show you how simple this is. So it's so easy to prove. You've got neutrons and you've got protons. Well, what is a proton? A proton is an attractive, positive chunk. And then you add just a little bit more to it, it becomes neutral. What do you have to add to it? An electron. It's all made of electrons. The whole thing is one ball of electrons. You add 0.0005485, which is between the weight of a neutron and a proton, and that's exactly what it is. So you're adding one more electron. They're just nothing but balls of electron. Now they think it's just one big solid positive thing in the center and some little tiny negatives out there. Absolutely, totally wrong. Never, ever. And well, let me tell you what Yale has to say. They agree. Okay, I'm going to let the professor here from Yale speak to his class about quantum physics and what we do and don't know. I couldn't put it any better than him. Here he goes.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So, all right. So that's.
It's tragic, but it's true. Right now, he has no right or ability to speak outside the system. If he did, they'd get rid of him. He has to say what they tell him to say, and the kids have to say what he tells them to say. Then they go back and tell some more kids to say what this guy told them to say. And, I have nothing against him, not at all. And he's being perfectly honest. He's trying to put the kids at ease. You cannot logically speak about this with the current model. It just doesn't work. They know it doesn't work. It never has worked. That's why they don't know what gravity is. They don't know where all the matter is in space. All it is attached to all the things that bounce back at you. It's the dark part. It's the carrier. Okay, let's see what else he has to say.
That's the spirit in which we are doing this. I want you to think about this as a real adventure. Try to think beyond the exams and grades and everything. It's one of the biggest discoveries in physics, in science, and it's marvelous how people even figured out this is what's going on. So I want to tell you, in some fashion, but not strictly historical fashion, the purely historical fashion is pedagogically not the best way, because you go through all the wrong tracks and you get confused and a lot of battles going on, and when the dust settles down, a certain picture emerges. And that's the picture I want to give you. In a way, I will appeal to experiments that were perhaps not done in the sequence in which I described them. But we know that if you did them, this is what the answer would be, and everyone agrees. And they are the simplest experiments.
Well, here's the problem. They're not correct. They are the simplest, but the double slit experiment, it doesn't work. That's just wrong. We use a single slit. We get the same results, only we actually can see the photons. So this is the problem. Everybody agrees, yes. They agree, but they're all wrong.
All right. So today we're going to shoot down Newtonian mechanics and Maxwell's theory. So we're like the press. We build somebody up only to destroy them.
Well, I'm not going to bother going any further, because he's right. Everybody had their own opinions, and they said, here's what it is, here's what it is. Well, it was all wrong. And it's all wrong because they started out with a gigantic positive core and negative surrounding it. Everything is a dipole. This is exactly what is the particles. Everything's made of this particle right here, these two particles, and they can separate. That's the key. They can separate, and the dark matter muon goes on its own way and becomes a sterile muon, and the white just becomes glowy, radiant showers. But almost instantly they come back together. So this is the true nature. There's not just one big gigantic positive and little tiny negatives rolling around outside. Absolutely not. Okay, all the particle colliders, they end up seeing these particles. The one, this is the tiniest ones they see, is a black one, never changes size, fixed particle, and a glowy one. And this is on Lincoln Fermilab. This is long ago, and we found exactly those particles. And he says in summary, extended particles have a fixed size, that's the black one, although may have a fuzzy edge around them. Yes, they do, which is a glowy. I'll show you in a second. Point-like particles are just mathematical abstractions with a zero size. So apparently there's no size to them, but they do have a field. So even zero-sized particles have an extended effect due to the field. Now I find it hard to believe there's nothing there, but it's possible. However, I can tell you, we found the particles, and here they are. All right, there's the Fermilab particles that they just drew pictures of. This is actually photons of light, of actual light, not smashing protons together and having huge debris piles. And seeing these, we're actually creating them and watching them develop and then split. And they do, they split just like that. They were glued together, they call them gluons. To me, each side is an electron. They're dipoles, they're like little bar magnets. And the only way we could separate them and break them apart and just destroy them is to put them through a venturi. A single slit. We still get all the same patterns that they talk about. And here's the particles. I mean, these are the particles right here. These are photons of light. That's 2 electrons back to back. And when you see them go through, this is the light right here. And the reason you have a wave and a particle is that particle that I just showed you up above has a field around it. This same particles. It has a field around it. So as it's going this way, you see these things are getting bumped here? I don't know if you can see that or not. See those little particles getting hit? Because of the field. The field is smashing into those particles. And then what it does is it creates a wave. It's as simple as that. I mean, it's just unbelievable. Because it's just like a magnetic field surrounding it. And that's what creates that wave. But the particles back here, all right, then it became so excited and accelerated. The particle itself started forcing the wave to crush. And then it sucked itself right out of the wave, and that's when it exploded and split. And that's it right here. This is fission, breaking apart of those two particles. And that is fusion, coming back together of those two particles. This is a single slit, not the dual slit, which everybody agrees on, which is or every one of them is wrong. We still have the same interference patterns coming out of here. They think it's a wave going this way through one slit and a wave going this way through the other, and that makes this flappy stuff. No. It's push to shove of these little tiny white glowy particles. They say, get the hell away from me. You get away from me. Say, okay, you stay in your line, I'll stay in my line. And they all stay away from each other and create the patterns. It has nothing to do with 2 slits at all. There's only 1 slit. This is as simple as it can be. This is exactly the laser used to create this pulse red laser. It's a Bosch GLM-15 construction laser. And then in the right backgrounds and so forth, you could see all of the particles that are in the air that have their own electrons. When they get bumped, they glow. That's what push to shove is. That's what glow is. That's what light is. It's pushing and then they shove back. Now, if they shove back strong enough, like here at the Venturi, we got a ton of energy. Well, what happened here? Pulse, pulse, pulse from the red laser. All right, here it is here. Now, it would have stayed like this, except it is in the line of the Venturi. The particle itself is right down here. You see these particles? Those are the particles that come out of the light. Each one of them makes a wave. Well, it's not specifically one of them, but they are in this line of particles. Let's just call it that way. Now, what happens at the Venturi? What is a Venturi? Well, the Venturi is a restriction. All this is a restriction. A very tight restriction here. And we did it with circular, like pins. A pin here and a pin here. Just round pins. Which means when the light hit it, it had to go around that and around this way, and poof! It smashed everybody to bits in the center. The black ones were just too big to get through. Can't get through. They can't shrink. They're the same size forever. Fermilab says yes. He says they're fixed particle. The other one is a point. It squirts down and it has no size whatsoever, they say, possibly. Now, we also accelerated blue and green and, and that's the colors of lasers that we had. Now, this is where the Higgs fields take off. Right here, you have nothing. All you have here is just raw electron showers. Which there's got to be something in there. Now they say they're just fields. I can't think. What's a field? A field is nothing without a particle. So there has to be. To me, there's got to be something in there, but I don't know if you can ever see it. However, you can see these little white zip, zip. I'm going to show you some closer ones. And then right out here, boom, they smash back into reality, which is to me where they hit the black particles and they go taking off and spinning like crazy. Now it depends on if it's red or if it's green or if it's blue, how fast they spin. The blue spins like hell. The red and the green, red is the slowest, the green is pretty damn fast, and the blue is just rocket ship. Now, I know I've shown these pictures hundreds and hundreds of times, but sooner or later somebody's going to pick up on it. Now, what are we looking at here? We're looking at light coming into the Venturi. The Venturi is here. That's where it explodes. It's just the particles of light, beep, 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 and then they start to stack up, and then they get brighter and brighter, and then they actually get spikes on them, and then they explode here. Now this is red. Green and blue is the exact same thing. All right, this is as simple as it could possibly be. The current model, which is called the standard atomic model theory, it just doesn't work. It never did work, because they have a gigantic positive core in the center, and then tiny little electrons on the outside. And then they go into all kinds of isotopes and ions and plasma and all this stuff. It doesn't work when you have that kind of a configuration. Protons are not one big chunk like that. All right, because they smash them into little tiny bits and pieces, and they find these two little black, they find the black and the red. This is exactly what Fermilab shows, and I will be showing you that in a second. Because they are not just one big ball here. They're made out of all of these. Which are those? One of these, every one of these dots is a magnet. You see over here? It's that magnet right there. There's the actual little bar magnet in the center. I just put it there. It's a ball magnet. And they hook up together in these balls like that, and at a certain quantity they become stable, and it appears in these periods, in these quantities. And there's like an electron is about hydrogen is about 1836, 1837, somewhere in there, of these little particles. It's not just one of these and one tiny little particle. No, it's all of these. All right, this is, and every bit of this, when you break up the hydrogen and explode them, you're not just breaking this apart. Hydrogen explodes like unbelievable, because all of these pieces come apart. That's why hydrogen is so explosive. There's so much to think about and to react to here in chemistry and physics and energy and light, and and I'm showing it all. I am not a theoretical physicist or scientist of any measure whatsoever. I'm a material scientist. If I can't show you something that lends a whole lot of credence to what I'm saying, I don't say it. Let's do a little credence. Okay, my friends, I'm just going to lay it on the line. Nothing is correct in subatomic physics right now. Everything is made of dipoles. Right now they say a proton is one big ball like that, and an electron is one tiny little ball that floats around the outside of it. One's positive and one's negative. That's not the case. What is actually happening is this ball, which they smash into bits, these protons, when they smash them into bits, they find these little particles inside, which are electrons. These are nothing more than electrons. But they're not the electrons as you think of an electron, which is just a negative little pushy, burny particle. What these are is electrons that have a dark side. And I show this in my experiments, and I probably already showed you, I imagine I have. The black side is dark matter. Nobody ever knew it was there. It's attached to the glowy side. And the glowy side is the electron. That's what pushes and shoves. This is the glowy side. The dark side is here. It's not, all it does is attract. You see these push apart? All right, the dark sides, they'll go grab right together and they'll ball right into a ball in the center. And all of the glowy parts, which are these, will surround that ball. You never saw the dark matter. Nobody's ever seen it. The only reason we saw it was because we broke apart light. If we didn't break apart the light, you don't see these dark, well, they see them at CERN. Let me show you or at Fermilab. Let me show you their work, and then you'll understand my work. But the nature of this whole thing is that there is nothing more than dipoles. And every single particle there is in the whole universe, I believe, is one of these, which is a dipole electron. Over here, you see, I put one of my little magnetic balls right in there. That's what they say is the magnetic field of a sphere, which is these. And balls of these together make up atoms. Atoms can attract, one big ball of an atom will attract to some other ball of an atom, and you'll have two of them hanging off together to make a molecule, and then they just keep, and there's, for some reason, I'm still trying to figure it out, why they stick together in these quantities. But I can see under the frequency on salt table experiments, they go zzz, and then they lock in at a very, very complex signatures. So I think it has something to do with that. It's a frequency. Why they're humming and buzzing, I don't know. All right, I'm not just doing this because I'm bragging, although maybe I'm bragging, but who cares? What we did was we accelerated the light and created these two particles that they are looking for, which is a muon and the electron neutrino. We found them. This is exactly what CERN and Fermilab were looking for, but they're colliding these huge particles together, and you're getting bits and pieces everywhere. We started with not protons. We started with this. We started with this kind of stuff. And it split and gave us a half of the electron, and the other half was the dark matter. You see it? They call it a muon electron neutrino, which is together, the black and the white. Showed it just above here, exactly identical to what Fermilab is looking for. You see the black? That's the fixed particle. You see the white? One's glowing, one's not. This one is glowing, is hitting the particles in front. It's moving to the right. It's going that way. All right? Now, and this is exactly what CERN and Fermilab have shown as well. There it is right there. This is the black one, fixed with a glowy edge. Yeah, absolutely. And this one here has no size to it at all, apparently. It's exactly what we found. Identical. No difference whatsoever. So I think Fermilab should engage. I've tried and tried and tried, and I have no success with that. This is, and I'm not just complaining that I'm not being heard. I'm complaining that we should be able to get free energy. If it reacts the way they say it does, they say it takes, let's say, thousands or even millions of electron volts to create this laser light. Electron volts, tiny, tiny. However, if you could separate and break the muon electron showers, which we did, supposedly this is trillions of volts, electron volts. So you go from millions to trillions. That's a huge increase in energy. And all we have to do is harvest it, because we could squirt it right onto a substrate. That substrate absorbs that energy, and we can use it for anything we want. And boy, I'll tell you, if we ever needed it, now we need it. All right? And we can, if you look at this carefully and understand what we did, you can see that wave has been accelerated due to this venturi, and the venturi is the key. It's got to be finely tuned and crushing of the fields. The fields are the things that crush, not the particles. The particles never touch. The particles never touch. The black ones are ejected because they're just too big. They're fixed. They can't get through. The whites get squirted through because they can squirt right down, as seen above here. You see the white and the black? This is exactly the words. Well, let me put the words into Don Lincoln's mouth as he wrote them on a piece of paper. Remember this picture. Remember that. That's our actual work. That's our actual glowing particle here and black particles there. All right? And this down here is the actual separation of those particles, which means fission when they broke apart. Come back together, that's fusion. We got a hell of an increase in energy, as far as I can tell. And if it was looked at least. It'll only take a couple of weeks to look at this. There's nothing here you have to develop. It's all off the shelf. It just has to be organized in the correct way and put something right here to harvest the output. All right, basically, Fermilab confirmed exactly what I showed. There's a black particle fixed, and there's the glowy little burny particle, and the field of particle physics is full of what can be confusing dichotomies. Well, there's no confusion here. It says, in summary, the extended particles, the black one, have a fixed size, although they may have a fuzzy edge. The point-like particles are mathematical abstractions with zero size, but even the zero-size particles have extended effect due to the field that surrounds them. Well, I believe there must be some little tiny particle, at least in there, that creates that field when it gets bashed into. The black one, he's right. Doesn't do anything. Stays just the way it is. This is precisely what I am showing for electron flood theory. No difference whatsoever. Only we see it. All the rest is theoretical. What happens with them is, like I say, we're working with light. We're working with light particles. There's just almost nothing there. There they are right there. That's where the electrons are, and that's where the dark matter is. It's just never been seen before. They're working with these protons and neutrons and big, heavy particles. And then they smash them together, and it's just like these things hitting, and everything goes flying everywhere. And they find these particles. Yes, absolutely, they see them. But then they see other ones that they see a lot of all the time. They see something that might look like that all the time. And then they see other ones look like that all the time. They call that their particle zoo, because there's a lot of little pieces that want to get back together, but in the meantime, they're all in little pieces. But the only thing is, they're little pieces of the same particles. All right? And as you get bigger and bigger, you get into atoms. And the atoms, the white particles will surround the core of the atom. It appears to me that black goes to the center. And that's been seen in space, in the Russians' space experiment. Well, I'll show you real quickly, because that's done with charged particles, nothing more than electrons that are charged little burny particles, and they glow. And then they pushed all the dark matter to the center. They freaked out.